Hello, everyone. Thanks for joining our webinar today. If you have any questions during the session, please submit them using the Q&A button at the top of the interface. Those questions will be answered at the end. This webinar will be recorded and you'll receive a copy of it delivered to your email account. I hope you enjoy the webinar. I'll now hand you over to our expert, Alex Blanche. Over to you.
Hi, everybody. My name is Alex Blasche. I have been working with Qt development for the last 15 or so years. And I've been I'm maintaining a couple of APIs, and I've been having my fair share of contributions to Qt in general. Today, I would like to talk about Qt CoAP, and which is a reasonably new API, which is introduced in Qt for Automation 5.13. Let's start. So to begin with, I'd like to give a brief introduction into CoAP as a protocol as it stands. Have a few. Secondly, would like to go into what Qt CoAP actually provides to you. And at the end of the day, I would like to do a quick, basically, I would like to compare MQTT and CoAP because they are most commonly, there's two protocols that are operating in the same domain space, but maybe not quite. Let's see how those two actually compare to each other. So what's CoAP? The Constraint Application Protocol. It's an M2M protocol, most commonly used in an IoT domain, and its focus is very much on minimal overhead and simplicity. So, in a sense, a single CoAP message is actually at the smallest version of it can actually be only 4 bytes, and its code size, if you want to implement that, is almost only 7K RAM, and depending on your implementation, maybe 100K of code space. Those are the minimum, the smallest versions that I have at least come across. So it's really something that you might be able to get into an MCU even in your thermostat or in other very extremely constrained devices. It's a client-server protocol, very much like HTTP, and in fact, CoAP borrows a lot of concepts from HTTP. The biggest difference here is CoAP is exclusively running on UDP. HTTP is mostly TCP-based, as you probably know. And CoAP tries to leverage the benefits of UDP, while at the same time adding a few pieces left and right, which actually, give you some of the convenience factor that TCP as a connection-based protocol can provide to you. It's an asynchronous messaging protocol, and its the main purpose here is compared to HTTP to have smaller packages, reliability, duplication on top of UDP essentially, whereas HTTP leverages a lot of those features already from TCP. If you're interested in the exact details, the main RFC for that is 7252, and then there's a whole bunch of further RFCs who basically add additional features on top. So how do a client and a server interact? So what's the server in this use case? The server is maybe the thermostat that has some temperature values, for instance, that it wants to broadcast. It maintains those internally, and whenever a client, that is the application that you may be writing with Qt CoAP, inquires about it, then it will basically return that temperature value, for instance, to the client. The entire protocol is designed around REST and RESTful the service discovery. The protocol essentially, I gave a few examples here. So a CoAP server can be basically addressed via a normal URL. In general, a CoAP server either listens on port 5683 or 5684, one being the secure version, 84 being the secure version, 83 the non-secure version. It also supports various ways of doing well, multicast and service discovery on multicast devices. When networks, multicast in networks to discover multiple devices as well. In general, once I've picked my device, there's a URI that is called well known, which then can be used to discover the services that this particular server offers, and then be able to further interact with those. Trade hallmark sign for CoAP is actually the extendability, and a bit more on that later on. So we talked about the core spec 7252 on the very right. It mostly, well, it defines the basic protocol, the basic messaging, how service discovery is to be done, how one can receive and obtain or push information to a server from a client perspective. And then the extensions, there's multiple RFCs who extend essentially the protocol with additional options. I've kind of mentioned the three most important ones from my perspective with the biggest impact, but there are one or two, a few more essentially. So maybe start with 7390. So there's the possibility to actually have group communication. That's mostly centered around how multicast and unicast responses from multicast requests across a network range can happen. And basically it creates the sense of we have several servers who contribute to a single client. Then we have an extension that centers around the fact that we might want to transport larger data. That's in particular interesting when we look at MTU values in networks. Some networks have much smaller max MTUs than others. And since we are wanting to go through a wide range of even low throughput networks, chances are that the network that you have your device running on might actually have a very, very tiny MTU. So this spec essentially adds the concept of, hang on, here's a big piece of data. I want to transfer this as efficient as possible. And for that purpose, I need to figure out what's the maximum MTU that I can keep running over this current network, as well as if I need to fragment it, segment it into larger, into several pieces, that adds the mechanism to say, okay, I've received the first part, now start from, give me the next 50 bytes, 100 bytes from offset X onwards. That's sort of the concept that is added here. And RFC 7641 adds quite a bit of convenience in terms of observing resources. So I can actually tell the server, hang on, when this value changes here, please let me know. In fact, you can even do interesting things via the URL where you can say, okay, if the temperature of my sensor of this value goes beyond a certain threshold, then start notifying me, otherwise don't. And then the option basically is defined with that RFC, and you can then basically create a more targeted solution. Another part that is also in this kind of RFC is the ability to basically avoid congestion or limit congestion on the device, on the network. There's certain expiry time frames defined, trigger definitions, essentially everything that is there to avoid an active polling. Let's have a look at the CoAP message. It's essentially the most minimalistic CoAP message that you can think of is exactly 4 bytes. That's basically the first line in this. So there's a version tag in the message. So far, there's only one version defined. Then there's a type. The type basically permits us to say, okay, please confirm the receipt of my message. So there's a confirmable, that's on the request side, and the server would basically respond with, okay, I acknowledge it, or he would say, the server would send a reset, which basically means, yeah, okay, I received something here, but it makes no sense to me. And the other option is the non-confirmable part, where we say, okay, yeah, it's a fire and forget. I may or may not get something. That's sort of trying to add some of the reliability into the protocol that UDP otherwise wouldn't give you. The token length is basically just an indicator of a token in the second line. A few minutes later, a bit more about it in a few seconds. The code that defines what it is that I'm requesting. What is it that, well, actually, what is it? That's essentially the message type. What it is that we want. It's usually defined as a sort of 3-bit, 5-bit, 3-bit, 5-bit pair. The first 3 bits basically tell you what type of request it is and or what type of response it is, and the second 5 bits give you a bit more details on that. Maybe jump to the next slide for that. Here I've sort of this comes straight out of the RFC, gives you a bit of an overview of what type of requests and responses there could be. So if the first 3 bits is a 0, then you're dealing with a request from a client, and typically a server will respond with one of those response values. And you can, when you look through it, you can see that not quite, but almost these values or these error codes or these response codes are related to at least the ones that you may be familiar with HTTP. Typically, if you, for instance, request get something, you basically get a 205 content reply, and that's probably the most common one in the bunch here. But all the other ones you probably are familiar with as well from HTTP. So that's what's encoded in the code section, and then there's a message ID, and the message ID is essentially supporting the type. So if you send some confirmable, if you make a confirmable request, then you get either an acknowledgement and reset. In order to match the request to the response, the message ID is used. That's basically the type matching. So every response to a particular type of confirmable must have a matching acknowledgement reset with the message ID, or none, if in case there is something in the network that isn't coming through. Then we have a token. So the token is actually a somewhat extended concept of the message ID. While the message ID is mostly referring to the type and matching those individual type requests and responses, the token actually matches connected requests as in code requests. So if you have a particular type of get request and you get later on you get a content request, then the content request that is matching that would have the same token. Or if you, for instance, have a block request where you have multiple parts chunked off coming one after the other, then there would all the responses would have the same message ID. Well, sorry, would have the same token, but the message ID for those would be actually different because you have a block request is typically also a pair of of request and responses. Basically, the first request would be give me everything from offset 0 to whatever your MTU length is, maybe, or slightly less. And then you get basically a message ID matching back with a token for that very same thing, and that contains the payload. And then you make another block request for the next offset, which has another message ID, but the token would still be the same because they also technically belong to the same block transfer, all individual messages. It can of course be 0 as well if it is not required. And then there's the big options field, and this is essentially where a lot of the extendability of CoAP comes from. It has very simple things like, for instance, URIs that you can define. You can define content paths, location paths, etc., etc. I would encourage you to just read it up in the spec. And almost all the other RFCs that I've mentioned earlier, they extend on this very same concept. So a block request or an observe request, those would be falling into the same category. And then last but not least, then there's a sort of a delimiter for the payload, and the payload follows afterwards. Good. Let's we talked about the requests and responses already, and we briefly mentioned the options that we have. So maybe just look at this in more detail for a very simple request. So here we have a GET request. This is a confirmable message type, so the expectation is that I get an acknowledgement. And in this case, it's a 0.01. If you may remember, that's basically the GET request. And we have a message ID that sort of allows the client to match the response against this request. In this particular case, we indeed have a temperature sender, so there must be some kind of path that on the other side, REST entry that basically, that's what is requested here. And this is, here you can see basically the content come back, T2.05, which is a content reply. The message ID corresponds, so the client knows what this is related to, basically to the temperature, and the actual payload is 22.3 degrees. Interesting, this is actually called a piggyback response, meaning the acknowledgement of the request and the actual payload are part of the same package. That is not necessarily a given. It is even possible to have a response that is basically an acknowledgement for the same message ID, and then have another response that comes through that says, oh, I'm a 205 content request with this payload. And in order to do that, that could actually be disconnected in a way. Typically, when you do that, you would also require a token so that the third message or the second response can be matched against the initial GET request. That is obviously missing here in this case. And here down here, you can see the breakdown how that looks like in the actual packaging. Oops. And then the package can basically be observed. Okay. Few things that's it in a nutshell for Qt CoAP, for CoAP as a protocol. We will have later. I will have a short demo, and we'll also look at how this behaves in real life. And but before we go there, I just want to mention a few highlights that you probably should be aware if you want to use Qt CoAP. So, as mentioned earlier, the library or the API was introduced in Qt Automation 5.13. It's most of the extensions that exist have been implemented. Most I mentioned, the missing ones you can see on the right here. So raw public key as a security extension, patch fetch, and CoAP over TCP WebSocket has not been implemented at this point in time. The central class for all your interaction is Qt CoAP client. It essentially has the put get methods that you would expect, fairly similar to what you might expect from a Qt Network Manager instance. And we have, there's also we didn't mention that so far, CoAP of course also has some security extensions that allow you to use some kind of authentication and encryption for the process. And for that, there is pre-shared key and certificate support. The third security extension is raw public key, which at this point is not supported. Qt CoAP is a client-side only API. It is not meant to be used to create your own instance of a CoAP server. For that, there's quite a few software solutions out there that can allow you to set up your own server. Good. At this point, I'd like to jump into a few practicalities around Qt CoAP. So I have actually opened here this simple CoAP client application. That's one of the examples that you may see here from the pop-up that comes with Qt CoAP. And it basically has, if I jump into the details here, it creates a Qt CoAP client, does the usual finish and error handling, and then further down, it basically, where we have it on one button here, it basically creates the get, put, post, and delete requests, the main request types that exist. Let's start that. So for my experiment, I obviously need some kind of CoAP server that to interact with. And what I'm going to use is actually a public test server, coap.me. In fact, if I jump over to my browser, you can even see that there's even a web interface for it, coap.me, and it's basically sitting on port 5683, and you can even basically query it via the web interface. It has various entries, which you see here. At this point in time, I'd just like to point your attention at the one that I'm going to interact with. This is the coap.me/validate. At this point in time, you can see there is this kind of string as payload currently defined on that branch or on that entry. And that's what we want to interact with. In addition, I'm going to also, so my client is running here. I have not done anything yet. In addition, I'm also going to start Wireshark and to actually, which is a very nice tool and to monitor what's ongoing. And I'm currently filtering by CoAP messages here. So let's start the entire process. So I need to, here's this well-known core discovery path that every server needs to support. And it returns with a reply that tells me what services and entries are available, most notably that what you saw on the website earlier. So it comes back as a REST response. And what you see here is sort of in detail is sort of the raw data, but what the app actually does, it kind of separates the individual resources with their capabilities, and so that I can actually interact with them. Good. So we have a validate, and when we run make a GET request against the validate, we get the string that we saw on the website. Now, interestingly enough, my Wireshark actually didn't show anything. That's excellent. Oh yeah, we have an error. Let's try that again. Continue without saving. And let's do the request again, discover. Here we go. So here I actually get now actually for my discover request also the entire communication. Let me get back to that in a few seconds. So you saw earlier we had the same string. Oh, by the way, here's a more nicer output of the discovery as well in this app. But that's the string that we have here. What I can do in this application also is make a put request or post request. I choose a put request. I'm actually going to add some content. I'm going to use a file that I just wrote here. It's called CoAP test txt, basically CoAP 1, 2, 3. And the application actually expects a file to be handed over. So I just nominated the file and basically run a put request. Put OK. That means also we can, here we see already a put request. Prior to that was something else. Get back to that in a second. And if I go back now to the website, I would expect here CoAP 1, 2, 3 in one way or the other to appear. So the CoAP test server acknowledges this, and the same can actually happen in the, if I just do a get request again to confirm the very same. So my request actually came through without a hitch. In the same way, good. Maybe let's have a look at what's happening in Wireshark, just to, because there we can very well see what it is that how the core protocol basically generates the messages, and it kind of also emphasizes the point that I had earlier in my package. Excellent, not so good. In any case, so I have the version. As you can see, my first request is a well-known core. So it's the option that it adds is the UI path for well-known, UI path for well-known and core. It generates a token and it generates an SSID and it says it's non-conformable. Cool, and it's obviously a get request. So that's what Wireshark actually nicely says here. And then the server essentially responds with a 2 or 5. It's again non-conformable, so the message ID doesn't really matter at this point. But you can see also the message ID is not matching for the 2. But essentially, it comes back and says, okay, there is a block. It has a size. There's a link, and it basically has a payload already. Good, and this is then how it continues. The first block, actually the first one was a block 0, and then it has a block 1, and it continues to fetch all the data, and there was quite a bit in the discovery until we get to here, where we basically have received the full extent of the payload, which in the end is essentially this dump that you see here in the app as a payload. And if you desire to do so, you can actually look at the raw payload data here as well. Good. Then the next thing, if you may recall, I actually had a put request. That put request was again non-conformable, and I actually had a data set here that is sort of the binary encoding of what it is that they sent, CoAP 1, 2, 3. And in this case, it again was non-conformable. It had a token number, and as you can also see, the response here is again in this case changed notification, changed response because there was already something there, and it has the same token, and you can basically, that's how the client can match the request against the response. And the second one was then reading back the value that I just wrote, typically a get request and then a 2 or 5 content request. In addition, maybe to just show the confirmable part of things. So I can actually take the confirm. Hopefully nobody else has written anything to it, so that this content should be the same. And yeah, it's oops, something is not right here. because it's not, oh yeah, my Wireshark was actually hanging. Continue without saving. Let's try that again, run. And here we go, now see that I actually get a connection, a confirmable request. So I'm requesting from the server that acknowledges my request for that given message ID. And you can see that the message ID here match. And then at the same time, it gives me the content as well. And that's why the token is again the same, because it's the request response matching here that is important. So what I wanted to show with that is that we have there's a small client application that we have that you can use to poke either a public server, CoAP.me, it works quite nicely. There's multiple other use cases on that server. Feel free to explore them and play around and get a bit of an idea what you can do. Some use cases you can do with this client, most notably the non-secure version, but there's also a client in the that comes with the examples that have then multicast, a bit more specific example for multicast and secure connections. And observe you can do as well. And in fact, you can actually also add some other options here that you might want to specify for your request. I can, especially if you're new to CoAP or you don't know exactly what's going on, I can very much emphasize the to use Wireshark because the protocol is so easy and trimmed so much on the bare essentials of what you might need for an M2M use case that it is very easy to figure out who is responding to what here and what might actually be happening in your network in case something goes wrong. Good. That sort of summarizes my demo section. Last but not least, I'd like to give maybe a bit of guidance, if I may, as to MQTT versus CoAP. When would I use what? What's their respective advantages or disadvantages? As with all things, really the use case makes it. And I could easily imagine that you actually choose one over the other, despite maybe the other one might be better because of some convenience factors that you can actually that you find in one over the other. So CoAP is really drilled down to the bare essentials, really constrained devices and networks, both essentially. You saw my earlier indication of what code and RAM you actually might need, and even the network part is you can basically run it over very unreliable networks with very, very low input, and the data package, the message or the principal message format also supports that as much as possible. Yes, by nature, it can basically recover as well. It's a one-to-one protocol, so you basically have a single client who collects from all the servers out there. So if you have an entire collection in an entire building of thermostats, you can actually run a multicast request. But at the end of the day, it's a one-to-one communication protocol. One client talks to each server, and then each server basically responds to back to the client. It's a very easy protocol, as hopefully you got an impression of. It's RESTful, so the things that you know from REST still apply. It does not have a broker. What is a broker? That's basically a concept that MQTT offers. Here, what happens is that your thermostat runs a small MQTT instance that, well, basically pushes the information that comes from your device into the broker, and then multiple clients, multiple interested parties in those values connect to the broker, who accumulates from the entire width of devices that you have set, and then essentially can hand out the data to whoever's interested. That certainly makes more sense, for instance, when you have multiple clients being interested in lots of other devices. You have one instance of a broker that can accumulate, and that kind of reduces the overhead that a single thermostat essentially has to put on the wire. On the other hand, the MQTT package is definitely a bit bigger. There's a lot of quality of service built into the protocol. So if you have really maybe a very, very tiny MCU-based device, you might find it challenging to actually get MQTT integrated into your device. QoAP might probably be a better way. But on the other hand, you only ever have to talk to one client as a device. You don't have to talk to many devices. That might also be a better way of actually safeguarding your infrastructure by saying, okay, everybody needs to go through a well-known broker, which can be adequately protected, etc. It's TCP connection based, so the benefits of TCP apply, and there's a lot of protocol comfort. Good. That sort of ends up the things that I would like to talk about. At this point, I'd like to close this session, and I wish and I'm hope that the conversation actually gave you the presentation gave you some details on how to proceed further with Qt CoAP.
Great. Thank you so much, Alex, for your great presentation. If there are any questions that you have after the session, please send us an email at info@qt.io and we'll answer them for you. But thanks again, and I wish you a great day until next time. Goodbye.